All right, let's look at number 2. We have the reaction up here, and they say the following results were obtained in experiments designed to study the rate reaction. So this is a pretty standard rate data table where they've varied the concentrations of 2 different species and tried to see what effect it has on rate. And so we're guessing that they're going to ask us the standard stuff, right? The rate law for the reaction, calculate the value of K, and so on and so forth. So this first one, right, the rate law for the reaction, we're obviously going to be looking for the format, but they're also going to want to know the orders since we have the data. Alright, so I'm comparing experiments 1 and 2 here. So we notice that as we go from 1 to 2, the rate doubles. So 0.04 divided by 0.02 is the change in rate, and that's 2, or the change in concentration. The change in rate, if we did 0.04 divided by 0.02, we still have to do 3.8 divided by 9.6. My copy looks like these are positive exponents, but it turns out they're not. They're negative exponents, so it should be 10 to the negative 1 and 10 to the negative 2. And when you do that, let's fix it up here, negative 1 and negative 2, this turns out to be 4. So that means that we have 2 to the n order equals 4, and so therefore n equals 2. It's second order with respect to NO. Now you notice that, remember, we don't want to just leave it as that. We actually have to explain what the 2 and the 4 are. And in the past we've said, you know, if you want to go ahead and just label the 2 and the 4 by writing words next to them, it's fine, or you can do kind of what I've done up here. So I'm going to find the order for the next one, which is BR2. Alright, so in the second one we're going to compare experiments 1 and 3. The change in concentration of bromine between 1 and 3 is doubling, and the reason I chose these, remember, is because the NOs are constant. You remember that there are some situations where you will not be able to find a experiment you can compare where the other one's constant. In a minute we're going to go over how you would deal with that. And so since we did 0.04 divided by 0.02 and we got 2 for the change in concentration, we're going to do 1.9 times 10 to the first minus first divided by this 9.6. You can see that was done here, and it was second. So the change in concentration was 2, the change in rate was 2, therefore we can say that 2 to the n equals 2, and in this case n equals 1. It's first order. So let's write the rate law. The rate law always is rate equals, and then what's that bit that people tend to forget? K. You got it. So let's see. K times concentration of NO, and its order is going to be 2, and the concentration of BR2, and its order is going to be first order. And we don't have to write the 1, but it's always nice to do so. The second part says calculate the value of the rate constant. Oh, wait a minute. Before we're going to do that, I was going to go back and show you, well, what do you do if you can't easily compare 2 experiments? You remember a lot of times one of the 2 reactants, you won't be able to do that. So let's remind ourselves of the rate ratio method. So the way we do the rate ratio method is we pick any 2 experiments where the thing we're interested in determining the order, so like let's say bromine, let's say we didn't have a direct comparison, where there's some change. You need to choose one where there's change. Like I wouldn't choose 1 and 2 because there's no change. So I'm still going to choose 1 and 3, but let's say this one did not, it also changed. Well, the way we do rate ratios is we take our 2 experiments and we write essentially the rate law twice, like this. So here's the format. Here's the rate law for experiment number 3 and rate law for experiment number 1, and then we're just going to plug in the numbers. The rate of experiment 3, the concentration of NO for experiment 3, which was 0.02, the concentration of bromine for experiment 3, which was 0.04. Then we're going to do the same thing for reaction 1 up here. Its rate, which was 9.6, its NO, which is 0.02, and its bromine, which is 0.02. So let's do that. Alright, so we've got all our values plugged in. Remember that K is going to cancel because it will be the same because it's the same reaction. These 2 over here, if you do 1.9 divided by 9.6 and its exponents, it comes out to be 2. So 2 equals, well, these 2 are going to cancel. But if they didn't, we'd figure out whatever number they divide to be. And then these 2 over here, well, 0.04 divided by 0.02 is 2, right? 0.04 divided by 0.02 is 2 to the x power. and then we can essentially, you'll notice it ends up exactly the same as it was, and we can figure out what x was. So that's the rate ratios method if you need it. Alright, on to part B. So I rewrote the rate law up here because we're going to need it in a minute. This might be a good time to remind you, I'm sure I reminded you in class, but that orders, the 2 and the 1, cannot be determined from the stoichiometry of the experiment. It just turns out to be coincidence that they're the same this time. You have to do a rate data table to figure it out. Actually do an experiment in lab. Alright, on to B. Calculate the value of the rate constant K for the reaction and include the units. So all we're going to do is we're going to pick an experiment. I'm going to pick number 1, and I'm going to plug in all of the data into the expression, and then I'm going to solve for K. Okay, so I've done that, I've plugged it all in, and I've gotten the value for K. Let's stop and look at sig figs. So let's see, up here we have 2 sig figs, there we have 1, and there we have 1. So we got to get this down to 1 sig fig. So I'm going to say 10,000 for the value of K. K, remember, can be quite big and can be quite small, so it's reasonable. Now let's do the units. The units, we essentially are going to put the units on these numbers that I left off, and we're going to solve for what the units for K are. So you remember that this one, and even if you don't remember, you can just look it up over here in the table, it's molarity per second. And we've got K there, and then this one is, let's see, for NO it's going to be concentration, so it's just molarity, but it's molarity squared because we had that little 2 up there. And then this one is just molarity because it's concentration. Now all we got to do is solve for K. So to solve for K, I'm going to divide both sides by m squared and m. So that's going to leave me with K equals m over s, and then these 2 are going to come down on the other side. So it's going to be m squared, and we got to have another m, which I'm going to put over there. And of course the m will cancel, and that leaves me with the m squared on bottom. So our units for K are going to be 1 over m squared s, or if we want to do it the fancy way, m with a negative 2 and s with a negative 1. On to part C. So in experiment 2, so we're going to be focusing on this one, what was the concentration of NO remaining when half of the original amount of bromine was consumed? So this is just a stoichiometry problem. And so they want to know, they're saying half the amount of bromine was consumed. Well, this 0.02 was the initial amount of bromine. And so what I'm setting up here is typical stoichiometry. I'm going to do a before and after table, but realize you wouldn't have to. There are other ways to do this. So initially we had 0.02 molar of this stuff and 0.04 molar of that stuff in experiment 2. I'm just making sure I didn't get it wrong. And we're not going to care what's going to happen over here because they just want to know how much of this NO is going to remain afterwards. So it's right here that really matters. So the change, they said half of this stuff was consumed, so it's going down by half of its amount, so it's going to have the other half remaining. And of course, if this one is changing by 1 time, this one's changing by twice as much. So instead of a change of 0.01, we're going to get a change of 0.02 here. So losing 0.02, and in the end we're going to have 0.02 left over. And I think that should be the answer. Let's look. In experiment 2, what was the concentration of NO remaining when half of the original amount of bromine was consumed? So yep, I think 0.02 is going to be the answer. We should check our sig figs, but everything else that we've used up above was the same, so I think that's the answer. I want to say 0.02 molar NO remains. Get units on it, get the sig figs, box your answer, and you should be good. And then part D, which of the following reaction mechanisms is consistent with the rate law established in A? So you remember, this is the data that is going to prove what the rate law was, and we actually, you'll remember that the rate law that we proved through this data was rate equals K times the concentration of NO to the second order times concentration of bromine to the first order. So this is the true rate law. It was determined through measurement of data. Remember, a mechanism is a hypothesis, and it needs to match the data. So there are two parts to it. One is probably the easiest one, which is when we get rid of intermediates, the reaction better add up to the total reaction, which is printed behind the rate law I wrote up here. So let's check that on both of them. So that's the first thing we got to do. So here we go. N2O2 is an intermediate. I'm going to get rid of it, and I think that's it. So we're going to have two NOs, which is true, and a bromine, yep, making two NOBRs. So it does add up to the total mechanism. Let's get rid of all that. So 1 passes the first test. Let's see if 2 passes the first test. And in 2, let's see, we get rid of some intermediates. It's kind of messy, isn't it? Well, we have a bromine on the right, and we actually have 2 on the left. You see this little 2 there? So there's 2 bromines, so we get rid of both of them. And we're going to end up with a bromine on the left, which it has, 2 NOs on the left, which it has, and 2 NOBRs, which it has. So they both pass that first test. Now, despite that fact, we need to say that as our first argument. All right, now our second check is going to be if they result in this mechanism when we look at the slow step. Because you remember, the slow step in each one is the rate determining step. And I thought I might do some markings on here, so you notice I made another copy up here. So let's move on up here, and let's see if when we look at the slow step, if it results in the rate law that we want. So in this first one, the slow step is this one. That's the important one. And so the rate law really would be rate equals K times the concentration of N2O2 times concentration of bromine. This we don't have to worry about. Remember, it's only reactants. But we cannot have an intermediate in there. So when we write the rate law, we're going to get rid of the intermediate, and we're going to substitute it with the two things that made it up. So the rate law for the first one would be, let's see, to kind of explain what I mean by that, rate equals K times N2O2, oh, I didn't leave enough room, times concentration of bromine, and they'd both be first order. You remember, we can determine the orders based on stoichiometry because these are empirical steps. They are not an overall reaction. Then we have to get rid of this, and then the rate law according to number 1 would be K times the concentration of NO, and that would be to the second order because there are 2 of them up here, and then BR2. And you'll notice that that does match pretty well this one, so I think the answer is going to be 1 is the matching one. We can try the whole thing on the second one down here. The slow step is the first step, which is which it would be rate equals K times concentration of bromine, and then that's it. And you notice there's no NO in it. So the second one's rate law according to the slow step doesn't work. And it's really important that we mention the slow step in our argument. Okay, so here's the argument. The rate limiting step from mechanism 1 results in the same rate law that was observed from experiment. And that, I mean, from up here. It might be better if you said from the initial rates data table. That would be even better. You would need the work that I did up here, but since I did it up here, I think I'm okay. And if you do not mention the rate limiting step, you will not get credit. If you do not mention that the result of it matches experiment, you will not get credit. Both of those things are important.